All right. Good morning, everyone. Welcome to the IvS seminar. So today we have Sven presenting, and his talk is probably the only one that is perfectly adapted to Belgium, because Sven is going to talk about clouds today, and clouds on planets, but unfortunately or fortunately exoplanets. Sven is a PhD student. He's doing a dual PhD between KU Leuven and Graz in Austria. So he's been, I think it's equally split, 2+2, right? And originally he comes from Zurich in Switzerland, where he did his bachelor and master's. And as I said already, so today Sven will talk about clouds on exoplanets, but I think more from the modeling than observational side of things, right? Yes. Okay, the floor is yours, Sven.
Okay, perfect. Thank you very much for already doing the one joke I always do in Belgium when I give a talk, because it fits perfectly. Usually when you can see outside, I can also point at the clouds because you can guarantee they're there. So I don't need to convince anyone here on the importance of my topic. We already have this covered. That's good. Yes, so as Andrew already said, my name is Sven Kiefer. I'm a dual degree student, so that also means I have a lot of collaborators, which you can here already see, which are all people that help me throughout the work and that I very appreciate. And today I'm going to give you a little bit more insight on the work that I've done during my PhD. But before we start, I wanted to give you a very quick second motivation, because even though clouds are present in Belgium, they are also, they are also everywhere. So if you look just at the solar system planets that we have, we can see them anywhere, like everywhere. Like we know from, of course, from Earth, our beautiful white clouds that do all these very nice patterns, but also on Jupiter's, we have all these nice colors and rings, which are also due to clouds. On Venus, we have them as well, Mars a bit, Uranus, and so on. Does anyone realize I cheated a little bit here? Probably. Does anyone have an idea what is missing? What? It's not to scale. Very good. Yes. But luckily, we're not looking at scales. We're looking at clouds. So the one thing, they're almost everywhere. So there's some cases where you have not really a cloud coverage as we would call them based on what we know from Earth. So we have Mercury, which doesn't really have one. Any other ideas where it might not be? We have this little friend. So for some people, he's still near and dear to our hearts. So Pluto also does not have any cloud coverage. And of course, our next door neighbor, the moon, also does not have really cloud coverage. But as you can already see, all the other ones have in some form or another clouds. So we can also expect that when we go to exoplanets, that clouds are important as well. Good. Then with that, I want to give you a quick overview, what I'm going to talk to you today. So first off, we're going to go a little bit into the basics. I'm going to talk a little bit more about cloud formation, and more specifically, how I used the theory behind cloud formation to gain more insights of their importance in exoplanet atmospheres. Then in the second part, I'm going to tell you more about the cloud optical properties, because in the end, that is how they interact with the radiation coming in and out, and is very much then affecting either the climate or the observations that we have. And then lastly, of course, I'm going to show you the impact of the clouds in climates, and I'm going to show you some climate simulation that we did as well. Good. Then with that, let's start with the basics. Let's start a little bit with the theory behind it. And before I go into how it works on exoplanets, just a very small recap from your high school classes, how it actually works on Earth. So on Earth, cloud formation starts with an aerosol, which we also call a cloud condensation nuclei, and which is basically just a small dust particle that originates from forest fires, volcanic activity, pollution. So there's a lot of possible origins for those particles. Once they are present in the atmosphere, and for example, you have this little scheme here, and the air gets lifted up, what happens is water becomes supersaturated in the atmosphere, and it starts to condense onto the droplet. Once the droplet becomes big enough, it actually feels the gravitational pull, it falls down as rain, falls onto the ground, collects in rivers, lakes, oceans, and then again can evaporate again and go into the atmosphere. And this gives you a cloud formation cycle. Now I want you to keep this this basic picture from Earth in mind, because as we will see, cloud formation on hot Jupiters, which I will be mostly talking about today, works similar but not identical. But it's already good that we are all now on the same page, so we can continue from here. Good. But then let's go to cloud formation in gaseous planets. Because one of the planets that we can observe best, that we know a lot about, are hot Jupiters, which are gas giants very close to the host star. So they have two things that are now, at least for this part, the most important differences to Earth. They are gaseous, and they are hot. Much, much hotter than what we know on Earth. So what we first have, if we have such an atmosphere, what we did model is the gas phase chemistry. And in this work, or for the first part that I'm showing you, we did consider a simple chemical kinetics network where we have N, C, H, and O, and a lot of, like, in total, 69 species and 780 reactions that we consider there. In addition to that, we added basically titanium and silicate reactions, because those, as you will see later, are important for the cloud formation in exoplanets. So this gives us basically the gas phase, the basics that we have. And then from this gas phase, cloud particles can form. And the first step that we have is nucleation, because as I already said before, on Earth, we have the aerosols, the CCNs, which can originate from the ground. But in gaseous planets, there's very little forest fires and very little volcanic activity. So they need to form directly from the gas phase, which is called nucleation. And it basically works similar-ish than the kinetic chemistry, but now we have an association reaction, which leads to slowly to larger and larger molecules, to clusters, and then to something that is the size of an aerosol. For this work, we consider TiO2 to be the nucleating species, but there's also some others that are sometimes discussed. Then, once we have the nucleation seeds, we can continue for other materials to grow onto, because some materials cannot nucleate themselves. So, for example, water in Earth has a very hard time to nucleate on its own, so it already needs these aerosols, and exactly the same way, other materials can only grow once a nucleation seed is present. For the materials that we consider, you can see here some examples, which is the ones that we considered for this study. And what I quickly want to highlight is there's two different kind of processes that can happen. On the one side, we have condensation and evaporation. And that means that the cloud material is already present within the atmosphere, and it can directly condense onto the cloud particle, or it can evaporate again, going into the gas phase. What we can also have is something what we call surface reactions. So those are more complex chemical reactions that use basically the cloud particle surface to collect material, which then allows for more complex reactions. And as you will see, they will come important later. So it's already good to distinguish those two cases. But both of them lead to the particle growing and becoming bigger. And then, exactly the same as we had it before on Earth, once they become big enough, they start to feel the gravitational pull of the planet, and they start to sink deeper into the atmosphere. So then we go deeper and deeper, and as I told you, those are hot objects, so the deeper you go, the hotter it gets, and at one point the cloud particle will evaporate again. So then we have basically material transport, things nucleate, they go down, fall in the atmosphere, and then give the material back, but deeper in the atmosphere. And again, if you keep in mind the picture that we have on Earth, that also means at one point we need to replenish again. Because now we have all the material further down, so some processes needs to be brought up into the atmosphere again. And that gives us a cloud formation cycle as we can expect it to happen in a gaseous planet. Not specifically exoplanet, but that's again what we're going to talk to a little bit more. Good. Now that we all have the basics of cloud formation in planets, and I explained a little bit more how we model the individual steps, let's look at an example. So this is, on the left, you can see the relative number densities. On the bottom, you can see time. And we always start on the left side in chemical equilibrium, and then we evolve it over time to the right side. And what you can now see here, those very nice straight lines, is basically just the case we start from chemical equilibrium, we give it the kinetic chemical network, but since it is already in equilibrium and there's no disequilibrium processes present at the moment, it will just stay in equilibrium. But what we're really interested in is what happens if we now couple the clouds to that. And the first step we're going to do is we're just going to look at the nucleation. So just TiO2 nucleating. No particles growing beyond that, just the nucleation. And if you have just nucleation, we can see two interesting things here. One of them is very obvious. You can see here the orange line, which corresponds to TiO2, and we see that we lose a little bit of TiO2 from the gas phase, which makes sense, because this is the nucleating species, so it forms into cloud particles, which are not considered here, because these are only the gas phase abundances. So we lose a little bit. But the second interesting thing is that we see is that it doesn't actually affect anything other. So all the other gas phase species are just there. They don't really are impacted by the nucleation alone. Now this image changes once we add bulk growth. So there's a lot going on. Let's quickly go through it, the most important things. So first off, we have species like magnesium, SiO2, or TiO2, which are all materials that can do bulk growth. So they can all grow onto the material. And if you look, for example, at magnesium here, the pink line, it just gets depleted from the gas phase. Not completely depleted. It will be somewhere very, very tiny percentage will stay in the gas phase, but it is significantly depleted overall. Same for TiO2, same for SiO2. Now, if you look at the other species, we can see some more effects. One of them, you can see here on top, for H2O and CO2, we can see a slight decrease. And that is also directly linked to the bulk growth, because through the nucleation, like a lot of the materials that I showed you before are oxygen-bearing. So when they grow, yes, we remove magnesium, but we also remove a lot of oxygen together with the magnesium. So what you can see here is basically a direct impact of the depletion of oxygen by the cloud particles. Now, there's one thing here that is a little bit more strange than that, because it makes sense that H2O and C2O get depleted, but CH4 is not an oxygen-bearing species. But if you look down here, we can see quite a difference. And looking deeper into that has actually revealed a very interesting mechanism that is happening there. And we gave it a very catchy name. We called it SiO2 cycle, which is basically a catalytic reaction happening through surface reactions of the cloud particle. But let me quickly guide you through that so that we're all on the same page. So let's assume we start with SiO in the gas phase, which then gets made into a cloud particle. So now we have SiOS. The S always stands for solid, so this is within the cloud particle. Now this SiO in the cloud particle can then react with H2 to form SiH and some H2O. Now this SiH then can use some water to go into SiO2 within the cloud particle. And then this SiO2 can then go with another H2 back to SiO in the gas phase. Now I can see you all staring very much at this cycle and like trying to figure out, okay, but what is actually happening? Well, if you go through the whole cycle, what actually happens once you do one turn, you disassociate atomic hydrogen into molecular hydrogen. So that is what it does. So you can see here, we have the 2H, and here the H going in. Now, this is still not entirely CH4. So we had a little bit of a closer look at the other reactions that we have within the network, and we found this set of 4 reactions. Because if you look up here, we have CH4, which can react with an atomic hydrogen to form CH3, then from CH3 to CH2, CH2 to CH, and then CH can then be locked up into H2CO. So basically, because of the interaction between the surface reaction of the cloud particles and the chemical reactions in the gas phase, we can then see how CH4 is affected by the presence of clouds. We analyzed this a little bit more. So where basically, this is a bit of a messy plot, but on the left you can see how much change there is due to this. So the higher up, the stronger this cycle, the further down, the lower. And then on the bottom you can see a range of temperatures, and in color you can see a range of pressures. So what we then found is, if you go to lower pressures, it becomes stronger, and it is most strong like within 1,100 to 1,500 Kelvin. The red cross points at where we were before. So the image that I showed you before is at the position that you can see here. Yes. And that already shows you that the cloud formation and the gas phase chemistry are linked together. So if you then start to consider, because oftentimes they are dealt separately, but if you actually consider how they interact with each other, you can reveal such processes that really need both the cloud particles and the gas phase, and how they can impact each other. Good. Yeah, that is what I wanted to give you for the basics on the cloud formation and how the cloud formation interacts with the gas phase. And this brings me to the second topic today. This is optical properties of heterogeneous cloud particles. Because as we already have seen, there's many, many different materials that can form clouds, and clouds in exoplanets can be potentially quite heterogeneous. And so we need to figure out a way to deal with that. Let's take, for example, here. On the left, you can see an interstellar dust grain. And first off, you can already see it's a very messy particle. It's not like the nice, beautiful raindrops that we know on Earth that every kid draws in their little books and then colors them beautifully blue. But in addition to that, we also don't expect it to be just water. We also expect it to be a lot of other materials. And then you can get these very messy particles. So then for this work, we looked a little bit at how people are actually dealing with these complicated particles in multiple different studies. And we found there are, I would say, 3 different approaches that are most often used. And we had a little bit closer look at them. So first off, I need to say, for all the stuff that I'm going to show you now, we assume spherical particles. As you've seen, they might not be perfectly spherical, and that has an impact. But for now, we focused on the spherical particle. And the first case that you can do is you can assume they're well mixed. Well mixed just means that if you look here, all the materials are very much distributed within the one cloud particle, and they're very dispersed. And in that case, you can describe the optical properties, in that case, the refractive index, with an effective refractive index, which basically just tells you, hey, what if we could describe this cloud particle with one property? And to do this, you can use 2 approaches, LLL or Bruggemann, which are the most common used for exoplanets, where they calculate the effective refractive index as a function of the refractive index of the different materials and the volume fraction they have. So the more volume, typically they are more important for the overall optical properties. As you can see, LLL has an analytic solution. Bruggemann is a bit more complicated and actually needs a minimization algorithm to be solved. But in the end, they were derived very similarly. But as I will show you later, unfortunately, that does not mean they're producing exactly the same results. The second thing you can assume is that cloud particles are more similar to what we know on Earth, where you have one thing basically forming the core, and then the materials forming a shell around it, which is also called then the core shell model, which then both of those are treated homogeneously, and again, we're assuming one sphere inside of another sphere. And the last approximation that is often made is homogeneous, where you can either assume that all your material is just every material forms its own cloud ensemble, depending, again, on the volume fraction. The more material you have, the more cloud particles you form. Or what we also looked at is, what if we assume that they're still mixed, but inside the cloud particle they are separated again. So they form kind of this homogeneous blobs within one cloud particle. Yes, and this basically sums up most of the assumptions that are currently made for heterogeneous cloud particles and the optical properties. So we looked a little bit closer into that. And unfortunately, it's a little bit of a messy plot, but don't worry, I'm going to guide you through it. There's a lot of information here, but it's also really cool what I can show you with that. So first, let's look at the plot on the left. What you can see here is on the bottom, the real part of the refractive index, and on the y-axis, you can see the imaginary part. Now, the real part is most often associated with scattering properties, whereas the imaginary part is most often associated with absorption properties. Now, this is not one-to-one. They do influence each other, but this is just for a simplified view now. Then what you can see here in color is the absorption efficiency, so how good a particle can actually absorb light. And you can already see we have here a little bit of a maxima, and then it basically goes out in all directions. And that helps us to understand a little bit more the optical properties of those cloud particles in a broader sense so that we can compare them. The next thing I'm going to show you here is this little dot here, which is basically where pure Mg2 SiO4 is, which is also called Forsterite. So I have the habit of calling it Forsterite, but I always mean this Mg2 SiO4. And where homogeneous iron is. So here, up here, this is purely iron. Now, the really cool thing, if we follow those lines, is basically how much volume fraction they have. So here we're pure iron, here we're pure iron, and then we go along this line, and the longer we go, the more Forsterite we have, until we end up at completely only Forsterite. And you can already see how messy it can get, because in purple, you can see the Bruggemann path, which is far from just a linear combination of the two. And on the other hand, you can see LLL, who does this kind of curve, which already shows us some very interesting properties. Now, before I go too much into detail, here you can already see again on the y-axis is now the absorption section. This is the same, just following this path, which helps us to compare it a little bit. Now, the one thing that I really want to show you is a little bit better if we go, to 1 micron, so the one that I showed you before is 7, now if you go to 1, because what we can see at 1 micron very nicely, same idea as before, is if you look at the path, actually the mixed material has a higher absorption than either of the homogeneous ones. So mixing material does not mean you're just mixing the properties directly or linearly in any sense, because then you would just be here on a line, but they really can change these properties because of the shape that you see here of this absorption. Now, the other thing that I wanted to show you is best seen if we go to 10 microns. And some of you might know why 10 microns and forsterite, they can make the connection. But for all others, it is honestly quite apparent, because if you look here, that means we are at 10 microns. Forsterite is very close to this resonance here. So that means we are at a pure forsterite particle, we have very, very high absorption. And then the closer we get to iron, we're quickly losing that, and then we're again having more of a mix between the two. Good. Yes, so as you can see, a little bit messy, but it also already shows that depending on how we treat the morphology of the cloud particle, it can really lead to different optical properties. So we need to be aware of that for the rest of the talk. Then what I also want to highlight, we chose here iron and forsterite. That is not without reason. Because if you look a little bit at the optical properties, and again, you can see here on the left, it works similar-ish as before. This is the volume fraction of iron in a logarithmic scale. So that means here we have 10% of iron, here we have 1%, 1 per mil, and it goes further down. On the bottom, you can see the wavelength range that we're looking at. So depending on the wavelength, the optical properties will be different, as we saw before. And then the colors basically indicate how drastically it changes. So blue means it is very close to Mg2SiO4, so forsterite. And then the more we go to the red, the more we're actually going to iron, where in the red one, we already changed the optical properties from forsterite way beyond what it was before. And the one thing that I want to focus you on here is actually the materials. Because if you look at iron, you can already see very, very strong impacts. Even at like volume of like 1%, we can already have a significant impact of iron. So tiny, tiny bits of iron will change your optical properties significantly. Whereas if you look here on the right with SiO2 and MgO, this is more moderate. Like there is some features that still poke through, but it's not as dominant as the iron inclusions. Perfect. Now that we know that, the next question becomes, what does it do to observations? And before we really dive into the full details, I want to give, again, a quick introduction. Imagine you are standing somewhere and you're looking at a beautiful sunset in front of you. And what you basically can see at the sunset is the sun passing through a lot of the atmosphere. And what you then see, the light that remains that you see is now influenced by this atmosphere, which makes it like this very nice blue color. Now, I did something strange with that image. Did someone realize what I did here? If I say this is a sunset. Oh, who said that? That is very good. This is exactly what it is. I'm very happy that someone saw that. This is actually a sunset on Mars. This is a sunset on Earth. Why do you know that this is a sunset on Mars? That is the point. There's not no atmosphere, but you're right, it is blue. And that is exactly the funny thing here, because the blueness is actually a result of the dust within Mars. And the redness here is then more of the optical properties of our atmosphere. So you can already see just those two planets, depending on the dust, you will get a completely different sunset. Now, if we just go 1 or 2 steps further, and further and further and further, further away, at one point we see this. So before that, we were standing here, enjoying the sunset. Now we are much, much further behind. And what we can now do is transit spectroscopy. So everyone who knows what transit spectroscopy is, you can take a 1-minute break. For everyone else, the idea in transit spectroscopy is basically when a planet passes in front of the star, it will block some of the light. But so will the atmosphere. And if we have just a normal atmosphere, it will just block all the light, but then depending on the optical properties of the atmosphere might absorb more or less light. So that means we then have a wavelength dependence of the observations. And if we then put this on a graph like this, where on the left side, we basically show the observed how much light gets blocked. So the further up we are, the more light is blocked, the further down, the less light. And we put this for different wavelengths, we get what we call a transit spectra. Now here we're going to look at the case of WSP-76b, which you will now later realize why it is such an interesting target. And we look at all the impacts of those different techniques that we had before. So we have Brookeman and LLL, which we looked a little bit closer. Just a reminder, SSA and BAS are just the two different homogeneous one, and then we have core shell. Now, unfortunately for WSP-76b, the full transit spectra, yes, we have some differences, but yeah. What we can do is we can separate the morning and the evening limb, and that becomes very interesting for that planet. Because what our models do, they predict that the evening terminator is basically cloud-free. So there's very, very little. There's some, you can see here, the deviation, so it's not completely cloud-free, but it has very little impact. Whereas the morning terminator is very, very, very cloudy. And there we can see two interesting things, again. The first, which you might know if you ever had to deal with clouds in, honestly, any form of optical radiative transfer, whatever, you can see that they block a lot of light, and thus they mute the spectra, so it becomes flatter, because it just absorbs in all wavelengths. But what you also can see is that depending on the technique, this flattening of the rest of this general, like this broadband absorption, changes depending on the technique. And this is not, like, those are not small changes. Those are quite, depending on what you define as significant, but they are within, now in here, you need to see. So they are quite significant changes. The second thing you can see is here around 10 microns, which again, if you remember before, our friend Forsterite has, at around 10 microns, comes very close to this absorption maxima. So what we can see here is the two peaks. But if you already look closely, you can only see the peaks if you either have core shell, and the yellow one is hiding here behind the other lines. You can see that here, the yellow one is hiding behind the green one, but it's basically following the green one as well. So the particles that are non-well mixed, that are separate, actually retain the Forsterite feature. Whereas if you have well-mixed particles, you will see they are much broader. So they basically just show either a broad or no feature at all. And that is really cool, because here we can see that the impact, the cloud particles and the morphology of the cloud particles have a direct impact on the observation, which can be very significant. So, of course, ideally, now with James Webb, we really hope that there will be some observations, which then will help us to further distinguish the cases here. Good. But with that, I already told you what I want to tell you about optical properties and how complex they can get and how they can impact our observations. Now, for the last third of this talk, I want to now talk about the cloudy climate of exoplanets. And again, before we dive into the big details, I just want to show you this picture again, because I don't know about you, but I found this utterly beautiful. The cloud structure that we have, just the patchiness, the different shapes and colors, absolutely beautiful, which fascinates me over and over again to study the details of the clouds. But as you can already see, is the clouds have a very three-dimensional structure. So it is not that we can just take one point and then tell exactly, oh, this is the cloud structure. They are three-dimensional, they impact the whole planet. So we did then also study analyzing on how clouds can actually impact the planet. And before I show you the results, the plots that I'm going to show you are basically isobaric maps. They have exactly the same idea as you can see here, where we have the Earth. Now, since we're looking at close-in gas giants, that means they are tidally locked, which means that the same side always points towards the sun. So, oh, that was the wrong button. So in all simulations, the sun is always here, smack in the middle. Not the sun, the host star of the planet is always here, smack in the middle. And the rest plot works exactly the same. So now let's put that aside, and let's have a look at Hot 6b, which is, by definition, a warm Saturn with an equilibrium temperature of 700 Kelvin. It has roughly the mass of Saturn, and it is, but it has the radius of a Jupiter. And then the host star is an M-dwarf, which are active, which probably a lot of people here know more than I do, because again, I focus more on the planet. And then we simulated the climate of this planet. And in the first iteration, we just did not consider any clouds. We just made a cloudless simulation using a general circulation model, which solves the fluid dynamics equation on a rotating sphere and thus gives us an idea about the climate. They are all originated, or most of them originate actually from Earth climate simulation and were then adapted to model hot Jupiter on other exoplanets. Now, hot 6b has the typical hallmarks of a tidally locked gas giant. We can see here, you will see it better in a second, don't worry. You can see here the hotspot offset, which is not exactly at the center, and you can see strong equatorial winds, which actually cause that. So even though the star is here, and most of the heat comes from here, because of the very strong winds, it is basically offset eastwards in that case. Yeah, so this is very much like what we would expect from such a planet. We then calculated a cloud structure and re-added this cloud structure as a static opacity source into the GCM run and run it again. And now you can already see some quite big changes. We can still see the hotspot, we can still see the offset, it now becomes much hotter, and we still see the winds. Now, of course, in here, the clouds are static, so they cannot react to these changes. So what we then did is, we calculated the clouds, we put the new cloud structure in, and you can now see some changes again. And we did this 3 more times. So what I want to highlight here is that if you look closely at the structure, it is not the same. And it also does not look like it converges to any specific solution. So we then basically ask ourselves, okay, but are those changes observable? So is the change that we see here still something that we can even determine through our observations? And as you can already guess, because we stopped at 5 iterations, there might be something there, but I'm going to show you this later in a second. I first quickly want to highlight some more impacts of the clouds on the climate. Now, what I'm going to show you next is the height, so the temperature pressure profile, and we take it at the substellar point of all the simulations. Gives us this plot where we have, on the left, we have the pressure. So we go from low pressures high up in the atmosphere to high pressures lower in the atmosphere. And on the X, you can see the temperature. The gray line here is the simulation without clouds, and all the colored line are the simulation with clouds. And before I'm going to explain a little bit more, I just quickly want to again refer to what we already know here from Earth. Because if we go to Earth and we look at this climate, and unfortunately, I was not able to take a Belgium example here because I needed a sunny day. So I needed to go to Sydney here. But what you can see is when we first have a sunny day and then cloud sets in, we can see changes in the temperature. And we can see 2 main effects. So first, during the night, it becomes warmer because the clouds can actually keep the heat where we are. Secondly, during the day, it becomes colder because the clouds actually prevent more sunlight from coming in. So you can see both how clouds can affect very locally the temperature. Now, if we go back to hot 6b, you can see here maybe something similar. Now, the second effect here is not that important in our case, but the first one even more so. Because what we can see here on top is basically those are the pressure level where the cloud opacity really start to become important. So that means a lot of the radiation gets absorbed here, and the heat is deposited here rather than further down in the atmosphere, which then leads to the second effect, which is an anti-greenhouse effect further down in the atmosphere. So it leads to both. So we have this cooling, this heating on the top and this cooling on the bottom, which causes this strong temperature inversion that we see here. Yes. So this is basically what we saw when analyzing the climate. Now, the question that I wanted to answer before is now, is this observable? Because you can see they are not identical. There are still changes. And we also not, like, even between 4 and 5, there are differences. So for that, what we did is we produced the transmission spectra, and we looked at the differences. Now, here again, similar to before, you can see the transit depth, you can see wavelengths, and on the bottom, you can see the absolute differences between 2 iterations. And we compare them to NIRSPEC PRISM and MIRI LRS for 10 transits of hot 6b. Now, between iteration 0 and 1, I don't think I need to plot the residuals. Everyone can see, yeah, they're different. That is OK. Now, if you go to iteration 2, it becomes much more tricky. Because if you see up here, they already look very similar to each other. So then we calculate the residuals, and we see that they are still above, but to be honest, they are already very close to the spectral precision of those instruments. So this is already difficult to observe. Not impossible, but difficult. Going from 2 to 3, we see a little bit of a switch up here. Now, two things. You can see there is some changes in the chemistry as well, but the big offset, basically the switch, like the baseline offset that you can see here, is caused by the clouds who are now becoming opaque at different pressure levels. Going from 3 to 4, we can already see, oof, that was quite good. We're basically hitting it. There's a small methane feature above it, but we're not, again, it's very close to the precision. Now going from 4 to 5, we can see very, very similar picture. So now here, at that point, we were convinced, like, if we would use 4 or 5, there would be very little difference in what we can actually observe. So we then took those as our solutions for the climate of Hot-6b. Now, the last thing in that talk that I want to show you a little bit more is I want to discuss the spectra a bit more so that you can actually know why this is so much interesting for us. Because if we now look just at the last one, so this is just iteration 5, you can see on top here, this is for the near-spec prism, and this is for the MIRI LRS range. And of course, there's a lot of cool things that we can see here, but I want to highlight 2. First off, CH4. If you look at this here, where the purple one is the total spectra, the gray one are the gas phase contributions, and the black one are the clouds, we can see, oh, CH4 actually peaks above, and there is a chance that we actually observe those features. Again, it is a bit tricky, everything, but it is very, very motivating to see that the clouds just not completely block out all the signals, so we are hopeful for some observations. Now, the second thing is the clouds. And on first sight, you might look at this and say, like, well, I put clouds here, but this is a straight line, like there's nothing. But if you look actually at the contributions from the different parts, we can see that the gas phase dips here quite significantly, while the clouds actually have a bump. And this bump might look similar to you. We saw it before. This is from the silicate. This is a silicate bump. Here we used LLL to calculate it. So we already saw LLL can lead to more broad features, or Bruckermann as well. I think in the other example for WASP-70, Bruckermann actually led to this very nice bump of those silicate features. And now you can see it more clearly, that actually the error bars here are very well within what we would potentially be able to gain a little bit more insight. So that we can actually see what the clouds, observe some of the cloud features within Hot-6b. Good, perfect. Then with that, I would already like to come to my summary slide. As I told you in the very beginning, we really went into the details of how the clouds affect the planet, how they interact with the gas phase chemistry, how they form. So you now know all the different steps that are involved to actually get clouds in gaseous planets, not just exoplanets, but in all gaseous planets. And you also know a little bit more about the intricacies of like hot Jupiters and what is happening there, and how clouds can actually affect the chemistry of a planet. We also saw some of the optical properties, where I think the main takeaway message is that the optical properties really depend on the composition and on the morphology of the particles. And so even though a lot of assumptions are made, those assumptions directly impact the optical properties, and you should be careful what to select. But it also gives us the possibility to learn more if our observations then go to the level where we can actually observe these differences, which is still a little bit ambitious, but not unrealistic. And then lastly, I showed you how clouds can affect the climate, because in the end, they are part of the climate. They were very much a very important opacity source, and they will have an effect on the climate, which will have an effect on the clouds and the chemistry and so on. Good. Then with that, I really want to thank you all for your attention, and I'm happy to take any and all questions.
Thank you, Sven, for a very interesting talk. Time for questions.
Yes.
Hi, Sven. Thank you for the talk. It was wonderful. I had a question about the last part. I think it's slide 70 or somewhere around that.
Yeah.
You showed the variability between the different iterations in transit depth.
Yes.
Is the difference there mainly due to the cloud distribution, the change in opacity from the gas phase chemistry, or is that just because you're dealing with temperature fluctuations on top of that?
So that's a very good question, because the answer is all of that. But they are different in different ways. So first of all, the cloud's distribution in itself has an effect, but it's linked to the other ones. Whereas the other two are very, very good observations. So the baseline change you can see here is, on the one hand, of course, caused by the cloud, where the clouds are actually located within the height. But this can also be a scale height effect, because depending if you're hotter, then of course your scale height changes, and thus your radiative your transit depth changes. So those two are linked here, because you cannot really separate one from the other. And then on the other point, the chemistry is also a very fair point. This is best seen here with the methane peak. Like, of course, also with HCN over here, but the methane is very clearly where you can see differences. And that is, so in this case here, the chemistry is post-processed on top of the atmospheric structure that we calculated. And so this is mainly a temperature effect that we see here. Because, again, the clouds impact the temperature. Temperature then impacts the methane concentrations. Yeah.
Thank you.
Hi, Sven. Thank you for this great talk. I understand that you're showing, like, looking for these observational effects mostly for transmission spectroscopy perspective. I'm guessing that the result would be very different in like direct imaging perspective. Can you tell us a little bit more about what would change to abort the problem in this direction, and what your work can bring to that?
Yes. No, you're perfectly right with that. So for the rest, to also give maybe a summary if you have not heard of that. So this is transmission spectroscopy, where we actually looked at the light that is filtered by the atmosphere, but you can also look, of course, from the light that is emitted by a planet, and then you will have, the clouds will also play an important role, but in a different way. Now, the very short answer that I unfortunately have to give here is we started to look into it, but we do not have yet the results here, because we already had a working transmission spectroscopy pipeline, so we were able to really do in-depth analysis here as well, which we did not have at hand for the phase curves and for the emission spectra. We did do some preliminary investigations here, and of course you have the typical effects of clouds that can, of course, change your phase curve, it can change your emission spectra, it can absorb some of the light, you will get different features, and so on. But I don't want to push this here too much, because again, I do not have concrete results, but we can talk afterwards a little bit more about what we already did.
Thanks. Thanks, Sven, for a nicely pedagogical talk. I'm not an expert in this field, but I had a question on your nice explanation of the catalytic reaction in the first part of your talk.
Yeah.
Can you bring up that cascade of reactions? What I was missing, and that's probably my ignorance. I mean, I understand the whole reasoning, but I wanted to know the time scales of these reaction rates determine completely what is the output. And so I wonder how you know them. Is that from extrapolation of lab results? And how uncertain is that impacting this diagram?
That is a very good question. Let me quickly see if I have it in the extra slides. Because you're absolutely right. This is very much linked to the timescale behavior. But I think, unfortunately, I do not have it in the extra slides. But it is in the paper. So those results are published. I can also then afterwards tell you, and I can show you there. But it's already apparent here. So these surface reactions, of course, happen, as you said, with a certain timescale. And that is also what we analyzed. And what you can see here is that the nucleation timescale, so if you can go one back, you can see is that the bulk of the nucleation happens here within like 10 seconds or even a bit lower, and then there's still some nucleation that happens afterwards. If you look at bulk rho, it basically immediately follows the nucleation. So as soon as you have something that nucleates, the reactions start to act, and as you can see, the reaction timescales are also on very, very short. So we're talking 10 seconds, 1 second or lower. But that then, of course, depends on where exactly you're in the atmosphere. It depends on your pressures, it depends on your temperatures, which you can see here, we took a very specific point. And that then leads to, it's a bit slow here, but that then leads to the plot that I showed before. where we actually, this then does this comparison, because this is linked to the gas phase and everything, to then actually tell you, okay, if we go to lower pressures, actually this becomes more important exactly because of that, because the time scale of this process suddenly becomes, oh, I was confused, shorter compared to the chemical one, whereas if you go to higher pressure, it is the other way around. Yeah, and same then with temperature as well. Yeah. But yeah, just very quickly, so in the paper we looked at different temperatures and pressure points, and there you can see even more like how the different timescales are and how the timescales of cloud formations are as well. There you can see it a bit more in detail. Yeah. Yes.
Hi, thank you for the very cool talk. I was wondering something about the optical properties. Maybe I just missed something you said. Can you go to slide 48?
48, yes, of course.
So you showed the difference of
yes.
the LLL and Brueggemann.
That one here? Yeah.
Yes. Can you tell something about, can you explain something about this, about the physical properties? Why do they give such a difference? Why in the red one you don't see anything and you see the feature in the purple?
Yes. So for that, let me quickly take you, let's take that one because that one's easier. There's less stuff on it. That all comes down to here and how you actually calculate the opacities. Now, if you use LLL or Brueggemann, you go along this path and you get a mixture of the properties. So you neither get the properties of forsterite or iron alone, but you get something new, which appears through the combination of the two. Now, if you use core shell, or if you use assume homogeneous particles, that's different, because then you basically get the contribution from here, and you add those together. So that is then more of a linear adding of the two properties. And that also means we still have that here. And if you then go to, honestly, this slide shows it best. That means if we assume homogeneous particles, we have these particles here, and we have this contribution from this very, very high absorption of forsterite. Whereas if we use LLL and Brueggemann, the other materials basically pull that away from this resonance and then make that this vanishes, because again, it's not a combination of that and that, but it is something new, which if you have homogeneous particles, it's just a combination of what you had before. With, again, core shell becoming slightly tricky because it can basically block some of the materials, but it's the same idea that it's happening there.
Okay, thank you.
Hey, Sven. Thanks for the talk. My question is a bit like, so you have your cloud formation scenario. If you want to start modeling this, what are the properties of the exoplanet and the stellar system that you do need to have a good handle of to be able to start modeling this?
Yeah.
And then the other thing is, if these properties also then come from transmission spectroscopy, how degenerate is the problem?
Yeah, that is a very good question. So in the end, it depends a little bit how much detail you want to have with the cloud formation. If you want to go for the most simple scenario, where you use just the thermal stability, you basically say, what can condensate will condensate. I don't look at the time scale. I don't look at the details. I just look at the stability of the cloud particles. Where are they stable? Where can they form? In that case, your cloud formation depends on the temperature profile that you saw before, not just a single temperature, but also on the profile of it. And it depends on the chemistry that you have there, on the elements that are, or the species that are available. So that is it at its very, very basis. So if you want to know cloud formation, you need to know at least this. Now, what we did here is actually a kinetic modeling. So we're not just looking at the stability, but we're actively modeling the growth and evaporation processes. And then you also need to start to take into account more effects, more of the motion. But then basically, the one-dimensional structure becomes very important. Like, where do the cloud particles fall? Where do you have more nucleation seeds? Where do you have less nucleation seeds? So the dynamics then start to play a role as well, which is here modeled usually in one dimension, where just assume you have the cloud particles, they fall, and then you get this dynamical aspect as well, on top, of course, of the temperature structures and the elements that can be there. And what was the second question?
Yeah, just where these properties come from, like if they also come from transmission spectroscopy now, for example, if you do manage to
What do you mean by these properties?
By that, I was actually meaning the general properties of the exoplanet.
Oh, the general properties of the exoplanet.
Even starting from if it's a rocky or a gaseous exoplanet, or I don't know, what are the other kind of properties you detect?
That's a very good question. And I like this question a lot, because in the end, it depends how much we already know. Because the more we know, the more precise we can model. So for those simulations here, what we used is we know from observations, we know the radius of the planet, we know the mass of the planet, we know, because it is tidally locked, we know the orbital period, and because, again, this means the rotational period has to be the same. So that already gives us, and of course, from the distance, we know the irradiation, and we know how much the planet is irradiated. Now, those we can use to model the climate of the planet. We then have to do some assumption on the atmosphere, where here we assume that the metallicity of the planet is the same as the host star. So we just use the host star as a proxy for the planet, which is not entirely correct, but that is one assumption that we made. And then with that, we also have the chemistry, and then we can use both those knowledges basically to then do the full modeling. But of course, the more details we have, the more details we can add here, and the better we can also check the models. And then it gets more and more detailed depending on what we know. Unfortunately, HOT6b at the very end that I showed you, it is already detected, but there's no spectra yet. But they are within JWST proposals, so I'm looking very much forward to seeing, to comparing what we did to the actual results and see how much of it we got right.
Thank you.
It's time for more questions.
Thanks, Sven, for this. How does the star spectrum, or the uncertainty on the star spectrum, fit into this? Because I imagine if you do transmission spectroscopy, you take a spectrum where the planet is over a spot, and then it's not over a spot because it's a magnetic active star, right?
Absolutely.
Or is this completely subdominant?
No, not at all. So there's two things that I want to separate here, because one is your actual question, and one where I want to hijack your question slightly, because you hinted at something that is very important for our work that we did. So first of all, for observation, no. Stellar activity is very much relevant for transit, especially, like if you want to detect the planet, to be honest, we're now very good, so the bigger planet at least you can detect through that noise. But if you look, that is exactly the question that I had. If you look at those differences here, this is like 100 ppm of a difference. So there you really want to have as precise measurement as you can. And there, this noise sources start to become very important. Because especially, like WASP-76, I'm not entirely sure what the host star is for that one. But for HOT6b is an M-dwarf, so that one becomes very, very active. And there, of course, you have much more effect. Now, the good thing is, M-dwarfs are also smaller. So that means, if we go to this here, no, wait, wrong one, this one here, you can also see that the differences are now much bigger. Because here we're now talking suddenly on the scale of like 200-ish and more, but the other one was like 100-ish in differences. Because if a smaller star just results naturally in a bigger transit radius. Now, the second thing that I want to mention is the stellar spectrum also impacts the chemistry of the planet. So, for example, for here, we considered photochemistry and stellar energetic particles that will affect the chemistry. And what we found is, I think this one I do have as an extra slide. Yes, this is here. Does it work?
Yep.
Oh, yeah, perfect. So this is the chemistry. There's a lot of things going on. But basically, this is just, again, higher up in the atmosphere, lower in the atmosphere, and how much we have of something. Now, let's just focus here on CH4 and NH3. And what you can see is this line here is the night side. So there's no photochemistry, no stellar spectrum.
Okay.
Then the dotted line here is just photochemistry, but no stellar energetic particles.
Okay.
And the full line is everything together. So here we have photochemistry and stellar energetic particles. And you can see is that actually reduces here your CH4 abundances in a pressure range where it's very much can impact your observations.
Because so it gets destroyed.
Because it gets destroyed, yes. So then this is also why we were quite happy to see this, because we can still see, yes, it gets destroyed, but we still have it. It is still there. So we still see it in observations. But no, so the activity, especially of M-dwarfs, is very much an impact here on the chemistry that we can may or may not
do you see this effect on, let's say, planets around G-dwarfs, or where it's maybe less?
Now you're stretching my knowledge about stars. What I can tell you is that we have observed photochemistry in exoplanets. So there is the effect of photochemistry that has been seen.
Good, thank you.
All right. I think we are at the hour, so let's thank Sven again. And just as a reminder, next week we are not going to have a seminar, it's a holiday, so we will reconvene from in 2 weeks from now with a talk by Olivier. Thanks for coming.